All right, let's get into it. Today, we're talking about Sunaba. And, it's not really a game in the traditional sense. Think of it more like a digital petri dish, a sandbox where brand new forms of life can actually emerge completely from scratch.
So let me just start with this one big question. What if that world inside your computer wasn't just some static background for a story? What if it was the primordial soup? A place with its own physics where creatures could literally spark into existence and evolve all on their own. That's the huge idea we're going to unpack today.
And this is the absolute key. See, in most games, the creatures are basically just digital puppets. They have pre-written behaviors, they're meticulously designed by artists. But in Sunaba, they are truly, genuinely alive in a sense. Their bodies, their brains, every single move they make, it's all a product of digital evolution, a direct response to the world they're born into.
Now, of course, if you want to have evolving creatures, you first need a world for them to evolve in. And that world can't just be a flat, boring stage. It needs to have real challenges, real physics. So that was the first massive hurdle, building a dynamic environment from the ground up. And here is where things get, well, kind of mind-bending. Most games apply physics to big things, right? Like a crate or a car. In Sunaba, every single pixel has its own physical properties. It's the difference between looking at a painting of an ocean and having a real functioning aquarium. So how is that even possible? Well, the magic behind this whole thing is a concept called cellular automata. Just imagine a giant grid of pixels. Each pixel or cell only has to follow a few super simple rules, like, hey, if the pixel above me is sand and I'm empty air, well, now I'm sand. That's basically it. But when you apply those tiny local rules to millions of pixels all at once, you get this incredibly complex, large-scale behavior that just emerges. And this is what you get. Out of those simple rules, you get a world that behaves in these predictable yet beautiful and complex ways. Sand piles up, it forms dunes. Water finds its level, it flows downhill. Fire actually consumes fuel and spreads realistically. None of this is explicitly programmed behavior. It's emergent physics. And it creates this constantly shifting, unpredictable landscape for our creatures to live in.
Okay, so we've got our dynamic world. Now we need the things that live in it. And that brings us to the next massive challenge. How in the world do you actually create the bodies for these artificial creatures? I mean, this is the fundamental problem, right? If you want a rich, diverse ecosystem, you can't just have a team of artists sitting there drawing every possible creature. You'd be there forever. You need a system that can generate an endless variety of body plans automatically. You need a system for creating biological blueprints. And the solution they came up with is this really clever two-step AI process. First, a special kind of network called a CPPN generates the initial body patterns, the blueprints. Then, a super powerful evolutionary algorithm called NEAT takes those blueprints and just runs with them. It refines them over thousands, even millions of generations. And here's the crucial part. NEAT evolves both the body shape and the neural network brain that controls it, together, at the exact same time. Let's look a little closer at that first step, the CPPN. It's a fascinating bit of tech. You basically feed it a location, like an X and Y coordinate, and it spits out an answer about what should be at that exact spot. Should be bone, muscle, or just empty space. By using different math functions, like sine waves, it can create repeating segments, like a caterpillar. And with other functions, it can create perfect symmetry. It really is like a digital genetic code for building things. So we have a system for evolving bodies. Fantastic. But a body is pretty useless without a brain to tell it what to do. And this presents a really unique and difficult problem when the body itself is constantly changing shape through evolution. I mean, think about it. If evolution suddenly gives a creature a new leg or changes the length of its arm, a traditional hard-coded brain would just break. It wouldn't have a clue what to do with these new parts. So you need a brain that is morphology aware, a brain that can instantly adapt its control scheme to whatever body it happens to find itself inside. And the answer is just brilliant. It's an AI model called NerveNet. It's a type of graph neural network that basically treats the creature's body like, well, a network. Information flows between the connected body parts themselves. So the brain isn't some central command center barking orders. It's a distributed system. If a new limb pops up, the network just extends to include it. This lets the same core controller work whether the creature has 4 legs or 40. It's incredible.
Okay, so we have a world, we have evolving bodies, we have adaptable brains, but there's one last huge trap we have to avoid if we want a real ecosystem, and that's the trap of finding the single best solution.
See, here's the problem with simple evolution. If you just set the goal to be the best, the algorithm is going to find one creature that's really, really good at one specific thing, say running super fast on flat ground, and then every other creature will eventually die out. You lose all the weird, interesting ones that might be slower but are amazing at climbing or fantastic at digging. You lose all that precious biodiversity.
The solution is this incredible algorithm called Map Elites, and it represents a complete shift in thinking. Instead of searching for the one best creature, period, Map Elites changes the goal entirely. Its goal is to find the best creature for every possible job. The best swimmer, the best digger, the best jumper, the best climber. You get the idea.
And this visual just says it all. Look at the left. That's a traditional search. It finds one or two good spots and then just gets stuck there, digging deeper. Most of the potential solutions are left completely unexplored, totally in the dark. But on the right, that's Map Elites. They call it an illumination algorithm for a reason. It literally lights up the entire map of what's possible, finding a champion, an elite, for every single combination of behaviors it can think of.
So how does it actually build that map? Well, it uses something called a behavior descriptor. And that's just a fancy term for a simple way to measure and categorize what a creature is doing. For instance, we could ask, how tall is it? And how fast does it move? Those two simple metrics become the X and Y coordinates on our map. And the algorithm can then file away the best creature it's found for every single spot on that grid.
Okay, let's pull back for a second and look at the whole incredible picture. We've talked about the pixel-perfect world, the genetic blueprints for bodies, those adaptable brains, and this map of elites that preserves diversity. Now, let's see what happens when you put them all together. Because the real genius of Sunaba isn't any single one of these amazing pieces. A lot of them are based on incredible academic research papers that have been around for years. The real breakthrough here is the synthesis. It's weaving all of these cutting-edge AI concepts together into one single, coherent, interactive, and evolving digital ecosystem. So let's just recap. What really makes Sunaba so special? It's that combination. You've got an emergent world where creatures can interact with every single pixel. They're built with these evolving blueprints and controlled by adaptable brains. And all of this is guided by an algorithm designed to create diversity, which opens the door for real coevolution, predators and prey. And on top of all that, it's meant to be a playable game, not just a lab experiment. And that really is the question that just leaves you on the edge of your seat, isn't it? The sandbox has been built, the digital DNA is ready to mutate and combine in new ways. The environment is there, ready to apply its pressures. All we have to do now is press play, wait a few thousand generations, and see what strange, wonderful, and completely unpredictable new forms of life manage to crawl out of the sand.